Okay, so in today's video, we're going to introduce the electrochemical gradient. And like in the previous video, focused on the idea of the membrane potential and voltage and simple electrostatics with how like charges will repel and opposite charges will attract. So what the electrochemical gradient is basically, since there's a potential that's being created across the membrane, we see a migration of ions that may be on the outside of the membrane going towards the inside of the membrane and vice versa. So this movement of ions, say I had, a positive, I'll just color code that. Say I had a positive ion here, and I'm moving, and let's see, say this is our cell membrane. And I have, say, this is the outside. I'll just label this like that. Out and in. If I have many positive ions and they're moving across this side from the out to the in, I'm creating an electrochemical gradient that favors positive movement towards the intracellular region. At the same time, I might also get some negative particles that are on this side moving across this way. So the gradient just refers to a flow of charge. So with the gradient, there's a simple problem that allows it to form a stable gradient, or something that's not freely moving. So this idea is known as the impermeability of the membrane. So the membrane is, let's talk about the membrane actually, because this is pretty important. So this is what the membrane is like. It's created by polar heads, like that, and it has nonpolar tails residing from the inside. So if I just get the right color, we have tails like that. So, because of the arrangement of this polarity over here, like this part is polar, and this part is nonpolar, and let's say this is the out of the cell and this is the inside of the cell. There is a property, or there's a general understanding that the only particles that will be freely able to permeate this membrane are small, like very small, non-charged particles. So these particles can easily move into the cell and outside of the cell. However, this does not hold when I have an ion. So an ion, for example, say I had, this was an ion, this is an ion. So if this is polar, this side is polar, it's just going to go and either stick onto this or be repelled back. So that's not going to really allow this particle to fully permeate through the membrane. Obviously, what the way these are like permeated is through selective permeability, where there are pumps. There are some ion channel pumps around here, and these are just proteins that allow the permeation of ions entering in to fully move throughout here. And on the other hand, we also can't have larger molecules. And I mean, this is pretty intuitive. If you have a larger molecule, it's going to be harder for it to get through because of, the structure. The rigidity won't be maintained, and so it's not going to be able to get through. And finally, our last example, let's say we have a water molecule. So we have a water, that's the oxygen, and these are the hydrogens. So if this is polar, what's going to happen is, since these heads are polar, there's going to be attraction or repulsion or electrostatics going on within these two, and this is going to become polarized. and there will be some intramolecular forces going on which don't exactly allow it to permeate through. So that's the understanding that ions cannot freely permeate through the membrane due to, like, to a certain extent. Obviously, electrostatics, say I have a heavy amount of, this is like a negatively charged particle and I have a lot of positive over here. It's going to be the attraction, if it's so big, it will permeate through, even though it's like, causing some disruptions in the, disruptions in the membrane. So now that we're done with that, we can also talk about basically how, since there is a gradient created, we can see that there might be a lot of positive charges, and this is what is true. We see a lot of positive charged particles. Here we go. We'll see a lot of positive charged particles on this side, on the outside of the membrane, and we'll see a lot of negatively charged particles on the inside of the membrane. And this might look similar because if you've taken a physics class before, this is basically an example of a capacitor, a parallel plate capacitor to be exact. This is one of our plates, and this is our another plate, and our dielectric constant is the fatty lipids. Fatty lipids. So if I were to say, try to mimic what a capacitor looks like in a normal, say, like a metallic circuit, this is generally the idea. This is a wire or some type of conducting loop that is transmitting current. This is one of the plates, a conductive plate, and this is another parallel conductive plate, and it's connected to the wire, and obviously it completes some circuit. And what's happening is there is a buildup of charge. So basically there's charge storage. On one you will see, say, positive charge. On the other you will see, you guessed it, negative charge. And between these two is what's known as a dielectric, where it affects how much energy you could store or how much charge you can store on this capacitor. And the way to find out how much is actually stored is through a simple equation that sums up capacitance. So capacitance is equal to kappa epsilon naught A over D. So D is this separation distance from the two plates, and kappa is a dielectric constant that characterizes the dielectric. So the higher the dielectric constant, the more capacitance, and the more it will be able to store energy. So usually what you might see in an electric circuit is that the dielectric constant is air, and air, the dielectric constant for that is just 1. So if you were doing this in like a regular surrounding, this would just be simplified to epsilon naught A over D. And now A is the surface area of this surface. So if these are my parallel plates, we want to measure how much of this surface is being used. So I'm taking the area of this area, of that region. And so that's just an understanding of how the membrane could be considered a capacitor. And there's another equation you could use to further understand capacitance and also relate it to membrane potential, and that is Q is equal to CV. And I'll box this around, where Q is charge, C is capacitance, I'm going to just simplify it to cap, and V is voltage. Okay, so far we have mentioned how the membrane could be a capacitor and what exactly the membrane potential is. And just to recap, membrane potential is just the difference in electrical potential from within the cell and on the outside of the cell. But now we can also specialize what type of membrane potential we're talking about. And in this case, we're going to talk about the resting potential. So the resting potential is a specific type of membrane potential. And as you might guess by the name, the resting potential describes the potential difference of the neuron while the neuron is at rest. And I'm going to define at rest because it might be a little bit ambiguous on what that means. And at rest means it is neither receiving nor transmitting any cellular signals. So that basically means that there's no action potential arising, and action potential, we'll get to that in a upcoming lesson, but that is the mechanism that allows cellular transmission, cellular signaling to occur. But the resting potential is basically when there's nothing happening. Like, I wouldn't say nothing, it's a stagnant cell that's not really performing any duties right now at that particular moment. And trying to distinguish between just the membrane versus the resting is also important, because obviously the membrane is a more general term and the resting is special or specific. But we can also define, okay, the membrane potential can go from, say, negative 90 all the way to positive 60 millivolts. And the resting potential, since it's specific, it can only go from negative 60 to negative 70 millivolts. And if you see, that's generally, this interval is within this interval. So it matches that the resting potential is a specific membrane potential. So also, let's focus in on this negative 60 to negative 70. What does that mean? So in the previous video, we talked about how the membrane potential is taken with the ground being the outside of the cell. Meaning, when I'm saying the resting potential is negative 70 millivolts, I'm saying that the inside is 70 millivolts more negative than the outside. Or I'm also saying it's 70 millivolts less positive than the outside. And if you wanted to say, okay, characterize, this could be like the outside could be 140 and the inside could be 70, right? If we're going to do in minus out, we're going to get 70 minus 140, which is negative 70. So that's a general understanding of the resting potential. And in the next video, we're going to talk about how scientists actually find the resting potential, how, like, what technology they use, and how they can stimulate that potential. So I'm just going to